So we don't have a full class today, but I was just planning on reviewing the microarchitecture stuff that I covered in the lab. I kind of hastily, on Wednesday, I gave a hasty lecture in the lab to introduce the next project. And then if you had Friday, we had the TAs give the same kind of presentation on a Friday. I think the TAs gave a shorter lecture than I did. So I'll just go over that again, make sure everyone's comfortable with that material, okay? So we talked about RISC microarchitecture, and we talked about RAM arrays. And RAM arrays are going to be used for our register file. So a RAM array is where you have an address that you provide it, and then you can read or write. And they are organized as a two-dimensional array of bits where you have a depth, which is the number of entries in the array, and the width, which is how many bits you can access at a time, right, in one cycle. And then you can have multiple ports on a RAM array. Each port allows you to do one access at a time. And sometimes those ports can be restricted to just being able to read, or sometimes they can read or write, or read and write. It all depends on how you code it up. And then once you code it up in Verilog and you synthesize it, you hope that there's something on the FPGA that will be able to, some primitive circuitry on the FPGA that will be able to implement that behavior. Now, in the case of the register file, I talked about how that has to have 3 ports on it, 2 read ports and 1 write port, which matches the instructions, right? The R-type instruction, essentially. The problem is that when you synthesize that on the FPGA, it actually ends up making a 2-dimensional array of registers with a mux for the output and a decoder for the writing part. You guys with me? Which is very inefficient because the FPGA has a relatively few number of registers. I think there's like 100,000 registers on the FPGA, but there's a lot more bits if you use a RAM. There's a lot more storage bits available on a RAM, but it won't actually target the RAM because the RAM has a synchronous read and it's limited to 2 ports. You guys with me? So in other words, what I'm trying to say is that you can implement a RAM behavior in Verilog, right? But that doesn't necessarily mean it's going to target a specific RAM on the FPGA. Sometimes you have to restrict yourself in the behavior of the RAM, right? Okay, so if that's confusing, hopefully I can clear that up a little bit. We talked about synchronous versus asynchronous reading. So with an asynchronous read, whenever the address changes, the corresponding data that's stored at that address is spit out immediately, right? It doesn't wait for a clock edge. That's an asynchronous read. The register file has an asynchronous read because we don't want to wait a whole cycle to read the register, right? At least not in our design. I think you can't afford to do that if if you have a whole pipeline stage for reading the registers, like you do with a 5-stage pipeline. But we have a 3-stage pipeline. So we need to be able to read the register values and send them into the ALU all in the same cycle. So we're going to use an asynchronous read. Does that make sense? Okay, and then writes are always synchronous, right? Writes always have to wait until the clock edge before the write happens. Okay? So what is the difference then? I have a timing diagram on the top that is an asynchronous read, and the one on the bottom is a synchronous read. And the only difference that you'll notice here is the read data. The read data is, on the bottom plot, is shifted 1 cycle to the left. So you're getting the data. Oh, sorry, actually it's shifted 1 cycle on the top, right? So the top, you're getting that data out earlier than you do on the bottom because you have to wait until the rising edge to perform the read operation. So over here, because the address is changing with the rise at the same time as the rising edge of the clock, when you have a rising edge of the clock and you change the address at the same time, the rising edge is reading the previous version, the previous value of the address, not the value of the address that comes up with the change, right? So that's the part that's a little kind of confusing here. So you can see the clock, we have a rising edge of the clock here. So in this case, if it's asynchronous, then we're going to be reading address 5, right? Because the clock goes up and the address changes to 5. That happens at the same time, but it doesn't matter because the point is that the address 5 comes up and it's going to spit out the value 5, which is at address 5. Whereas down here, you have a rising edge of the clock. The address changes to 5, but what's happening there is you're actually reading the address at 4, right? So the RAM is going to see the previous version of the address there, the previous value of the address, right? So that's why we have 4 here. So this 5, reading 5, happens on the next cycle. So 5 gives us 5 on the next cycle, right? Address 5 gives us data 5. Right? I initialize this so the data is the same as the address, so I could, illustrate that. Okay. Alrighty, so I showed the register file design. So this register file has a RAM array here. Remember that when you declare the RAM array, it's opposite. It's opposite of like everything. Right? You put the width first and the depth second. Don't do that in C. Or Python or Java. And then there's 2 assigns here for reading that implement the read ports. Actually, I think the one that we give you in the project skeleton might actually do this with an always statement, but it doesn't matter. The logic is basically the same. The read ports can be implemented with combinational logic because they're asynchronous, and then the write is done with an always FF down here. Okay, so you can just use that register file in your design. Register 0 always holds 0, and if you read and write the same register at the same time, you're supposed to get the new value that you're writing, right? That's the register bypass. You guys, does that make sense? Okay. Then we're going to give you this arithmetic logic unit that is capable, I think, of like 13 operations, but there's 16 opcodes. So some of these opcodes are redundant. Like, for example, 1101, 1110, and 1111 all do the same thing. A less than B unsigned, right? They're all the same. Same thing here. 1010 and 1011 are all a write arithmetic shift. Okay, so basically there's, in the RISC instruction set in MIPS, there's one R-type instruction for each of these operations. And then some instructions use these like indirectly. Like, for example, a branch instruction will use the comparison, even though you're not doing a set less than, you're doing a branch, but the comparison opcode is used to resolve the branch. Make sense? Okay, so, but mostly these ALU functioners are used for R-type and I-type arithmetic logical shift and comparison, and number crunching instructions. Okay, and that's the code for the ALU. The ALU itself is mostly in just this one assign statement with ternary operations, and then there's some additional code over here. The shifter. Yeah, I forgot about this, right? The arithmetic right shift. Remember the right shift, you shift right, you shift in the sign bit, right? There's supposed to be a Verilog operation for that. Greater than, greater than, greater than. But for some reason, I don't actually remember what the story was with that, but it didn't work for us for whatever. We couldn't use that. So instead, we put this always block in that looks at each bit of the shift amount and uses blocking assignment statements here to say that if bit 0 is set, we're going to shift by 1 bit. If bit 1 is set, we're going to shift by 2 bits, possibly in addition to shifting by the 1 bit, right? So that way, if it's 1, 1, it's 3, then you will have shifted by 1 bit, by 1, and then by 2 to get 3, right? So, and then so on and so forth, all the way up to, so you can shift by 1, 2, 4, 8, or 16, depending on which of the bits are set in the shift amount, or any combination thereof, right? Yes?
Always begin and always combinational.
Oh, right. So always combinational is whenever you have your intent as a designer is not to have memory, not to have sequential logic. So that's just used as a way to tell the compiler that, right? So if you accidentally put a latch in there, it would generate an error, right? That's all that means. It's the same as saying always at star, right? Except it has that additional check. And then the begin and end is there just whenever you have multiple lines If you only had one line of code in there, you won't need the begin and end, right? And that also applies to if statements too.
Yeah, I was just wondering if that.
Okay. So I don't know if any of you can figure this out, like why we couldn't just use the Verilog operation. I'd love to know. Also, the signed multiply was a little weird too, the way we did that. We said assign, we had to type, so logic apparently, I didn't know this till we did this, but in Verilog, logic is treated as unsigned. So if you do a multiply operation, or even a less than, I guess, right? Yeah, less than. You see that less than? It's treated as unsigned. So if you wanted to treat it as signed, you have to typecast it as signed. So we had to do that for the signed multiply high, as well as the signed less than comparison operation. It's weird, but I guess it kind of makes sense because, but I guess there's probably a way to declare a logic as signed initially, but I don't know how to do that. Okay, so we're going to implement 22 instructions in lab 3. And there's 3 different types that we're going to use in lab 3. In lab 4, there's another encoding format, I believe, in the next lab. But for this lab, there's only 3. There's R-type, I-type, and U-type. R-type is all the instructions are under the R-type are listed here. So obviously, most of the R-type has the most instructions in it. Basically, is just whenever you have a 3 address instruction, meaning 3 registers, a destination and 2 sources. And then I-type is when you have an instruction with 1 source register, 1 destination register, and an immediate, right? The immediate is only 12 bits, though, which is different from MIPS. But then there's a U-type that has a 20-bit immediate, and that's only used for 1 instruction, the load up immediate, or 1 instruction that we're implementing anyway. Make sense? Now, you might say, why 12 and 20? Well, the idea is that if you want to load a 32-bit value into a register like a constant, then you use a combination. Use a load up immediate to get 20 bits in, and then you follow it up with an I-type to get the other 12 bits in. And between the two, you get 32 bits. Any questions about that? Okay. Also, I mentioned last time, but there's these function fields, function 7, function 3. I-type has the function 3. Kind of a confusing format. So like, you have to figure out what an instruction is, you have to check the opcode first, because that's the only field that's common to all the encoding formats. And depending on the opcode, then sometimes you have to also look at function 3, and then sometimes you have to additionally look at function 7, right, to figure out what the instruction is. It depends on the instruction. And I'll show you an example of that that you can use, or a way that you can code that in just a minute here. Okay, and then we talked about the CSRRW instruction. So we have 2 registers here, I/O registers. I/O 0 is the keys, and I/O 2 is the hex display. So if you read from I/O register 0, we want your CPU to read the key values. Switches. Switch values, the switch on the board, right? So we're going to read the switches for I/O 0, and we're going to write the hex displays on I/O 2. So either way, you're going to use the CSRRW instruction. The CSR register, which will be 0 or 2, is always the second operand there in the assembly code. And then RD would only be used if you're reading the switches, right? And RS would be a don't care in that case, right? Because if you're reading the switch values, you're going to put the switch values into a destination register, so that source register is a don't care, right? But if you want to send a value to the hex displays, then the source register would be the register whose contents you want to put out to the hex displays, right? And the RD would be a don't care. Does that make sense? Now, in reality, that's not true. In RISC-V, those are both actually used always, because in RISC-V, it does like a swap. It takes the control register, it puts it into RD, and then takes the RS register and puts that into the control register, right? But we're not doing that. We've hacked to this a little bit, just so we can, make it work with the boards, right? And in the case of the boards, we're gonna, the switches can only be read and the hexes can only be written, right? Okay, so this is we used to have by the way we used to do this before RISC-V, in MIPS, we used to use register 30 for that. If you had any instruction, didn't matter what the instruction was, but if it wrote to register 30 as the destination, it would update the hex displays. And if you read from register 30, you would get the keys. But that was more hacky, right? We were like mapping register 30 as a special register, right? And we had to implement that in the register file. That was a little too hacky. I think this is a better solution because it takes advantage of a real instruction in RISC-V. Okay. Okay, so then I talked about the top level design. So I started putting together, because this lab is always, it's always a little hard to get started on this lab because, it's like, where do you start? So I started coding this up just to show you guys how to, kind of how to start. So I started with, so I downloaded the lab RIW skeleton. RIW refers to the, the RI and U type, RI and U type instructions. And I started with a module line for CPU. And there's 3 inputs. There's clock, reset, N, which I'm using an active low reset because we want to connect it to the keys, and the keys are active low. You don't have to do this. You can have an active high reset. I don't really care. I think it's easier to have just the active low coming in. So what the reset does is, if you get a reset, the only thing it does is it resets inside the fetch logic. It's going to reset the instruction to zeros, all zeros. And it resets the program counter fetch to 0. Right? Now, actually, I just thought of this. I forgot about this. We had an issue with this. So, what is this supposed to be? All zeros for the instruction. That's supposed to be a no-op, right? It's supposed to be an instruction that doesn't do anything, right? In MIPS, that is a no-op. Why? Because in MIPS, 32 zeros actually maps to a shift-left logical instruction with a shift amount of 0 and a destination register of 0. So it does nothing. You can't write to register 0, and even if you could, it wouldn't actually change anything because it would take the contents of register 0 and shift it by 0 and put it back into register 0. You guys with me? But RISC-V does not use all zeros for the no-op. RISC-V uses like an add instruction, but the problem is the add instruction has a function 3 code that is like 0, 1, 1. Right? So I just thought we might want to, actually, well, it doesn't matter for you guys because you can just put a line in your control unit and just treat this as a no-op. So it's not a big deal, right? But might want to revisit that. I just thought of that now. That's one oddity that's come up in the past. But that's meant to be a no-op. And then, of course, the fetch, you want to start fetching at 0. So when you hit the reset button, that's basically the reboot button. And just like any computer, when you reboot it, when you reset a computer, it starts at PC 0, which is going to be your power on self-test, and will eventually boot up the machine. You guys with me? Okay, so that's all the reset does. It doesn't touch any logic except for that. Okay, and then we have a input for IO0 in. Can you guys read that? Okay, let me make that bigger. That's too much. That's too much. Okay, there we go. Okay, is that more readable? Yeah. Okay, so IO0 in and IO0 out IO0 in is going to be hardwired to your switches, but there's only 18 switches. So how are we going to, I guess you're going to have to 0 pad that, right? Put like zeros, right? 14 zeros and then 18 switch values, right? But we have a 32-bit coming in and 32-bit going out. We do need all 32 bits going out though, because those are going to go into 8 7-segment decoders, right? So you guys have your 7-segment decoders. So each of the group of 4 bits in IO2 out are going to go into one of the 7 segment decoders, and the outputs of those are going to go to hex displays. Okay? Okay, then we have the instruction memory, which I declare here. You can make it deeper than this if you want. I usually use 4,096 instructions deep. We have more memory than that, but your programs will be like 100 instructions or so. But if you have 4,096 bits, then your program counter has got to be the log base 2 of that, which is 12 bits, so 11 down to 0, right? And then you can read, you can initialize the instruction memory with hex code or program.rom or whatever you want to call the text file that you're going to dump your RARs to. Your RARs code, right? RARs, the code, the software, right? And then we have instruction EX. I don't know why it highlighted PC fetch in red. Strange. But instruction EX is here. So this signal corresponds to the address of the whatever's being fetched. And this corresponds to whatever instruction has already been fetched and is now in the execute stage, the second stage. That's why I'm being careful to use these suffixes. And then below that, this is something I mentioned last lecture. You guys don't have to do this. I think it's helpful, though, for debugging. But you can come up with alternative signal names. So instruction EX is whatever that's the machine code instruction. But then you can rename the fields of it appropriately so you can see what's going on, like what the fields are, right? So like for example, RD, so there's RD destination and opcode are the 2 fields that are common to all 3 instruction formats. So, and then their register source 1 and function 3 are common to the R type and I type, right? So you can declare those. So you could declare those fields with the appropriate size, and then you can just use an assign statement to strip out certain bits from the instruction and assign them there. So this line of code is not going to use any hardware. There's no logic here. It's just, you're assigning an alternative name to a part of instruction EX. So this doesn't cost any gates or wires on the FPGA. So this is free. It's something that's just there for, the benefit of you as you debug the code and as you write the code, as you design it. So I think it's pretty nice. You can also put this, you don't have to inline this. You can put this in its own module if you want. The problem is that if you do that, every one of these guys, like function 3EX, is going to have to be an output from that module. So the input will be instruction EX, and then you'll have like 1, 2, 3, 4, 5, 6, 7, 8 outputs. So there's 8 different fields would have to be spit out of that module, which is kind of a pain because then you have to wire all that stuff up. But on the other hand, it's probably better than just having all this in here because it starts to get a little unwieldy with all this code in here. You guys with me? Okay, so that's up to you. You don't even need to do this, by the way. You could just, instead of immediate 20, you can just use instruction EX 31 down to 12. Okay, so then there's something else I like to do to simplify the debugging a little bit. You can declare, and I haven't showed you the syntax yet, but you can declare a type, a Verilog type. This only works in system Verilog, by the way. I don't think Verilog doesn't have this. This is a system Verilog exclusive feature. But you can create a type called instruction name, which is an enumerated type, and you can put the mnemonics in there of all the instructions. And so that way, the control unit can assign a signal to be one of these types, and then when you're looking at the waveform, you can actually see what instruction is in the execute stage. Does that make sense? And again, it's free because that won't affect the hardware. That's just something that would be for simulation purposes. Okay. Okay. So then I started the control unit. So the control unit I did it as an always COM. And so I have a default output, instruction in EX. I'm going to set it as unknown initially. Because that way, if you fetch an instruction and your control unit doesn't know what it is, you'll know it immediately because in model sim, you'll see unknown there for the instruction. But then if the opcode is 3, 3 and the function EX is 0 and the function 3EX is 0, 0, 0, then the instruction EX is add. So I'm sorry, I said that wrong before. The add instruction is the no op, but it's not the function 3 that has the non-zeros, it's the opcode. But anyway, that'll give us our add instruction. Now obviously I haven't filled that in, I've only assigned that one meaningless signal, right? Eventually I have to go and assign all the other control signals, which in this case is going to be the ones that are in my table down here, right? So these are the other outputs that you want to have in your control unit. It makes sense? Okay. Right. Okay, any questions about that? Does that make sense? Okay, so let's go ahead with, oh, and then there was that test program. We talked about that, I think, last time. So we have a test program for you somewhere. Yeah, right here. So we have a test program that just tests every instruction once. So how do you know if it works? How do you know if the test program works? Well, normally you'd have a self-checking test bench that would somehow check that, right? But how would that work? Because the test bench would be testing the CPU, and if you have a design that has the CPU in it, how would that design know if the CPU is working? Well, there's really not much you can do aside from using that CSRRW instruction and having it output something visible to the outside world that would let the test bench know that it's working. The other way to do it is to run it in model sim and just look at the contents of the register file, right? And so you can look in the register file and check to see if it matches up to these comments are the answer key, essentially. These are the values that should be in the register file after each one of those instructions is executed. Okay? And then the other test program I mentioned was the binary to decimal conversion. So the idea with this is you're going to put switch values in, and then it should print the decimal version on the hex display. Any questions about this? How this works? So we're going to use fixed point again to approximate the divide by 10 and modulo by 10. Okay? Okay, so let's take a look at how you get this program in here. So if I take the test program and I copy that, and then I run it in RARS, Java, jar, RARS. Okay, so we got RARS, and I'll say file new, and I'll paste that. Okay, so looks good. Save this as RISC-V ASM, hit assemble, go to file, say dump memory, text, and hex, I think, hexadecimal text. I think that's it. And then we'll call it, what did I call it? Terminal. What I call it? I called it hexcode.txt. All right, so, oops, sorry, back to here, back to RARS, and say hexcode.txt, and just put it in the root directory. Okay, so then I'll go back to here, and we should be good to go now. Okay, so I'm going to go ahead and run it and see what we get. So we'll do vsim. Oh, well, first I'm going to type vlog cpu.sv, and we're good. I'm going to type vlog cpu. Sorry, vsim cpu rather. Okay, so this is vsim or QuestaSim, and so you can see the top level signals here, but you don't see anything inside the CPU. So we got to go to simulate, start simulation, optimization, apply all visibility. I used to know how to do this at the command line. I don't remember how to turn that on now. Okay, anyway, so now we're good. Now we have the CPU and I've got all the internal signals there. So I'm just going to bring all those guys over here and I should just be able to run it, except I don't have a test bench, so I'm going to have to manually set up the clock. So I'm going to right click that clock and say clock and hit OK. And then the reset, I'm going to set, I'm just going to do that down here, force reset underscore n to 0, run, force reset underscore n, sorry, RST underscore n to 1, run. Okay. Is it working? Yeah, looks like it. So you can see that, where's the zoom? Zoom. Oh, here it is. Oh, here it is. Yeah, got it. Thank you. Okay, so IO0 in is a blue line, high impedance, because I didn't assign it. I didn't drive it. It's not driven by anything. And IO2 out is a don't care, red line, because it's not connected to anything. So because this is an input, it's blue. It's an input not set, it's blue. And signal not connected to anything is red if it's not driven. Then I've got the instruction memory here, which if you hit the plus sign there, it'll actually show you the contents of the instruction memory, but it's, it's 4,000 entries deep. And then you can see the program counter. So generally when you first start up, there's a couple things you want to look for. Number one, look for a heartbeat. The heartbeat is your clock. So make sure you got a clock. If the clock's not running, everything's just dead, right? So we got a heartbeat. Then the next thing you want to look for is the program counter. So the program counter fetch is 0, 1, 2, 3, 4. You can see it counting up. You can also see that it was 0 for 2 cycles because I had a reset cycle, right? So the program counter was 0 for the reset, and then it was also 0 for the first cycle of operation. And then after that, it counted up. And then you're going to get an instruction stream coming out. So the instruction EX, check it out. You can see 1, 2, 3, 4 instructions have popped out so far. So those are the first 4 instructions of the program. If I look at RARs, if I go back to RARs, do I know? I don't have it? I don't. Oh, there it is. Yeah, so the instruction is, the first instruction is 00C00093, right? Do I have that? Yep, there it is, 00C00093. And then 0110013, 0110013. So you can see that there's a correspondence between that instruction column and the instruction stream that's coming out of the fetch stage into the CPU. So you can follow along in ModelSim. You can follow along with RARs if you want, if you want to, check all what's happening in the register file. And speaking of the register file, if we want to see I don't have that in here, so I can't show you that. I didn't add the register file yet. But you can once you put the register file in, you can look at the contents. You can drill down into the register file and you can add the memory. Is it memory? Mem. It's called mem or something. The signal that's declared that holds the 2D array of bits. Just put that in ModelSim and you can see all the values they're updating. And there's only 32 of them, so it's you can fit 32 registers on your screen here. With the instruction memory, it's too big. And of course, you can check that if, like, for example, if you're not getting anything out of instruction mem, there's a chance that ModelSim couldn't find your initialization file. So you might want to check. In that case, you could look at the instruction mem here and scroll down and just confirm that your instructions are in there. And you can see I've got them in there. How many do I have? I've got 25 instructions in there. And addresses 0 to 24. Okay? Okay. And then what about that little instruction in EX? Oh, there it is. Check it out. Instruction in EX down here. This is that thing I declared that's the enumerated type. It says unknown because apparently, well, the only thing I have support for right now is the add instruction. And so where does the add instruction show up in the code? It is, oh, it's like, uh-oh, it's the third instruction. Well, that should have popped up then, shouldn't it? Am I not seeing? Oh, there it is. Yeah, it is. It is there. You see that? So I got unknown. So I got unknown up until the third instruction, and then there's an add there, and then another unknown, right? So the control unit is working in the sense that it's recognizing the add instruction, which is not trivial because I had to check 3 different fields to figure out if it was an add instruction. Any questions about that? Okay, so basically then to finish this CPU, really all you have to do is we have to put the ALU in and the MET register file, and then you have to finish the control unit, essentially. So that involves filling in what's going to be a giant if-then-else statement in here, right? So you're going to have, so if I want to add another instruction, like let's say I want to add the add I instruction, I can, so I can say, now I'm going to put a begin here and an end, and then I'm going to say else if. Now for the add I instruction, that's an I type. So for how do I recognize an I type? Well, basically I have to look at the opcode and the function 7, but not the function 3, right? Do I have that right? Oh, what did I just do there? Copy and paste. What the hell is it doing? I'm not in, oh, it wasn't in insert mode, I guess. Here, let me try that one more time. Paste. Nope. I don't know what's going on there. All right.
Maybe because it's Lima stressing.
Usually it doesn't. I don't have an issue with that. But that's okay. I'll just go opcode EX equals. Okay, so what is the opcode for? How do we figure out the opcode for add I? Well, if you go to Dropbox, there is some stuff here you can use. There's RISC-V ISA official version. That's going to be a train wreck, I think. Yeah, that's going to be too many details. Let's go, not that. Sorry. Let's go to our version of the RISC-V ISA. Yeah, so here we go. So we'll go add I. Add I, come on, add I, there it is. Okay, so it has a function 3 of 0, and it has an opcode of 1, 3, it looks like. 1, 3, right?
Yeah.
So 1, 3, and 0. Okay, so 1, 3 here, and funct 3 EX equals 3 binary 0, 0, 0. Begin, and just to test this, I'm going to say instruction in EX equals add I, and end. Okay, begin, end, and I need another, oh cool, okay. So that works, and then I have to add the add I to my enumerated type list, right? Because I just have, yeah, I don't have add I in there, so I'm going to say add I here. Okay, and then go down to here, and vlog cpu.sv, and I'll go back to Questa. I hit restart, and I got to set up the clock again, so I'm going to up arrow to the clock command, I'm going to up arrow to the reset, and I'm going to hit run, up arrow to reset again. This is why it's nice to have a test bench, because you don't have to do this. And run for, say, 400. Okay, so yeah, so now you can see the instruction in EX has now been updated here. I've got add I in the first 2 instructions and add in the 3rd instruction. So the control unit recognized the add I instruction. So now if you go in the control unit, you can add the additional code that you need to implement the add I. So if you go up in there, you can say, you can add ALU source EX. Now I didn't declare that yet, but ALU source is going to be what is the mux setting on that ALU for the second input, which is I don't have that here, do I? ALU, oh yeah, right here, over here. ALU source EX is supposed to be 0 for the register and 1 for the immediate. So in this case, it's going to be 0, but in the add I's case, it's going to be a 1. Does everyone see that, why that is? So this is one of the differences between, actually it's the only difference, I think. Well, yeah, it's the only difference between add and add I. It's just the ALU source. Everything else is the same. Now, of course, you have to set, like, the ALU op is going to be the add. I want to tell it to add. Well, how do I do it? How do I do that? Well, you have to figure out what the ALU op for add is. What is it? 0011. So I can set the ALU op to be 0011, and I want to do the same thing for the add. ALU op EX equals 0011. So those will be the same. And then the other thing is reg write back. Oh, sorry, EX. No, yes, EX rather. It'll become write back in the next cycle. That's going to be 1 because both of these guys write a register. So reg write EX equals 1. Now remember that the register file's write signal is going to be reg write back, because there'll be a register, or flip-flop rather, in between reg write EX and reg write back, right? So I'm going to set reg write EX in this stage, and that means in the next cycle I want you to write the register, but don't do it now. Do it when the add gets to the write back stage. What else do I have in here? ALU op, ALU source, reg select. Reg select is going to be, where's the reg select? This guy, this mux here. Reg select is what I'm writing back. So in both cases, I want the ALU output, right? You see that? So the ALU is going to provide the sum, and I'm going to take that, I'm going to delay it 1 cycle, and then I'm going to pass it through here. So reg select EX is going to be 2, right? I'm going to select the ALU output. So reg cell EX equals 2 in binary, 1, 0, and reg select EX equals 2 in binary. And that's it. I think that's all. Oh, yeah, and the one last thing is the there's another signal in there that's reserved specifically for the CSRRW, and not just any CSRW, but the one wherever you use register 2, IO2, I think. Yeah, that's the output IO2, right? So if I have a CSRRW and the IO register address, which is the immediate field, which is the 12-bit I-type immediate, if that's 2, then I'm gonna enable this thing, which I called GPIO write enable. Why does that not have a suffix though? That should have a suffix, sorry. So I'm gonna give it a suffix. I'm gonna say GPIO write enable. I'm gonna call it E. I'm gonna put a suffix on there. And that should be 0 in both cases, because neither one of those is neither one of those instructions updates the hex display. Okay, any questions? That makes sense? So and again, that control unit could be in its own module. You don't have to inline it like I did. If you inline it, you're going to have your CPU.sv is going to be really long, right? But you could put that all into its own module. It makes the code a little cleaner. But you have to create another file for that. Make sense?
Figure it out when I start crying on it. Yeah. Probably a combination.
Okay, so we have there's a quiz. Quiz 3 is up on Dropbox. It basically covers this. Like, it just asks you what the control signal should be for different instructions. I think this Friday. Let's do this Friday. So make sure you take quiz 3. It's up on Dropbox. Okay? All right, we'll see you in lab then. Thank you.